Hello everybody, what's up? So I haven't been able to upload any videos in the past, think 2 to 3 months, and that's because a lot of the things were going on simultaneously, and I couldn't really find the time to make any videos. But now that some of the stuff that was previously going on is no longer going on, I can somehow take out the time to make a video when there's a good video idea. So this is like a sort of an update video, although it's not like a getting back to uploading videos video because um, I'm not really sure if I will regularly get the time to make regular videos. So I cannot really promise that there will be a video every week. But whenever I have a good video idea and I'm in the mood to make a video, I will make one. And on another update, I started reading a new book. It's called Solving Mathematical Problems, A Personal Perspective by none other than Terence Tao, which, by the way, he wrote this book when he was 15 years old. So, that's something impressive in itself. I'm excited for this book because it's interesting to look at the thought process of a 15-year-old prodigy. And I came across a problem in this whose solutions was um, interesting enough. So that's what we're going to look at in this video.
Let's go.
So the problem is from Taylor 1989. It's problem number 37. And it asks the question, is there a power of 2 such that its digits could be rearranged into another power of 2? And just note that no zeros are allowed in the leading digit. So for example, 2 to the power 5 is 32. You cannot write it as 003. The first digit has to be a non-zero number. So let's go ahead and write a few powers of 2. There's 2, 1, 2, 4, 8, 16, 32, 64, 128, 256, 5, 1, 2, 1024, 2048, and okay, that should be good enough. Now, how do you start off with a problem like this? I mean, of course, to start off with any problem, the first good thing is to make some observations so that you understand the problem. In this, it would be a good idea to essentially keep on reducing the problem until you either reach the fact that yes, there exists, or you reach a contradiction, in which case it doesn't exist. So here, one simple but, as you will see, key observation to restricting or reducing the data is to see the following, that if we take a look at, let's say I take a look at 256, right? It's made up of the digits 2, 5, and 6. Now, of course, in the ones that I have listed here, I know there's no rearrangement of 256 that will give another power of 2, right? And in my thought process, I can see that I only need to look at these two other results because these are the only other three-digit numbers. Because if I move way too backwards, I will enter the realm of two-digit numbers and one-digit numbers. And if I move way too down, I will enter the realm of four-digit numbers. So I know that for any number, if a rearrangement exists, the number of digits must remain the same. So like if 652 is one of the rearrangements, but that's not a power of 2. But if there exists such a power of 2 such that its rearrangements give another power of 2, then the number of digits must remain the same. And so this seems something that's very workable because let's say if I have anything like 2 to the power n, 2 to the power n plus 1, then there's n plus 2, then there's n plus 3, right? Now, at this point, it is completely possible that if I go from here to here, it is possible that 2 to the power n plus 3 contains the same number of digits as 2 to the power n plus as 2 to the power n. But if I move one step further, let's say 2 to the power n plus 4, I can say with certainty that this right here will have less number of digits than 2 to the power n. And if you want to see it explicitly, because 2 to the power n plus 4 is 16 times 2 to the power n. So which is 10 times 2 to the power n plus 6 times 2 to the power n. This will obviously contain more digits than 2 to the power n, so it's useless to look at the case which are 4 more than that power. So for any certain power, I really need to look at 3 above it, or I could say 3 above it and 3 below it, because if I make jumps of 4, then the number of digits will not be the same, which means that the rearrangement cannot exist. This is excellent because now we have reduced the number, or we have reduced the data that we need to take care of. Now we really need to do something about, you know, how will we check whether a number has the same is the rearrangement of another number. Well, one way to check it is to check its digit sum. Now, when I say digit sum, I mean the sum of their digits, literally. So the digits in 256 are 2, 5, and 6. So its digit sum will be 2 plus 5 plus 6, which is frankly, well, 6. This will be 13. And the reason why I think this might be helpful is because if there's a certain rearrangement, let's say 652, its digit sum will be 6 plus 5 plus 2. But since the digits are the same, then this will also be equal to 13. Right? So this is the second key observation that we've made. The first one was this. So now we have changed the problem into saying that, okay, so does there exist a power of 2? And we're only looking at 3 above it and 3 below it, such that its digit sum will be the same, right? So let me write out a couple of digit sums just so that the idea is clear. Let me write with golden. So this will simply be 1, 2, 4, 8. You know, you have 0 plus 8, 0 plus 4. That doesn't really change anything. Now 1 plus 6 is 7, 3 plus 2 is 5, 6 plus 4 is 10, 1 plus 2 plus 8 is 11. This we already calculated, it's 13 right over here. This should be 8. This should be 7. And this should be 14, I believe. Yeah, it should be 14. So when we look at this pattern, well, it's not really a very nice pattern. It looks very random. And, in the general sense, this will increase because the number of digits that are available will increase, so its digit sum will also increase. But that's on a very general basis, and this won't really help us. We can see that, okay, so at the starting it was increasing, but then it dropped, and this sort of randomness seems to continue. Now, there's one last crucial step that will help us solve this problem. And well, frankly, I couldn't figure out that last step. This is as far as I made it to solving this problem. But if you want to pause the video and try to figure it out, I think it would be pretty satisfying to figure it out yourself. But that last step is really to look at modulo 9. So if this seems completely out of the blue, one thing that I would recall is that you might remember the divisibility rule of 9, that if there's a number whose digit sums add up to a multiple of 9, that thing is divisible by 9, right? So, and this already gives us the hint that 9 is somewhat of a special number when we look at divisibilities and digit sums especially. And so for example, 81, the digit sum is 8 plus 9, which is a multiple of 9. This implies that this is a multiple of 9. And if I take anything like 82, well, this is one more, so the digit sum will be 10, which is like 9 plus 1. So this is like one more than a multiple of 9. Right? So the observation here really is that the number modulo 9 is the same as the modulo 9 of the digit sum. And to show that explicitly, if you have any number, let's say the number is an minus 1, so these are the digits, you're not multiplying, these are the digits. This is the same as 10 to the power an plus 10 to the power n minus 1 an minus 1 an minus 1 all the way to 10 to the power 0 a0. Now if I take this number and take its modulo 9, well, the thing is that 10 is the same as 1 modulo 9, and this is why these two would be equal when you take modulo 9. So 10 is 1 mod 9 because 9 plus 10 is 1 away from multiple of 9. So then if I do 10 into 10, which is 100, this would also be 1 mod 9. So any power of 10 is always 1 mod 9, because 10 is 1 away from 9, 100 is 1 away from 99, 1000 is 1 away from 999, and so on and so forth. So all of these coefficients, they become 1 to give you an plus an minus 1 all the way to a0. So you would realize that when you take mod 9 of the number, that gives you the same value as mod 9 of the digit sums, because you're adding up the digits here. So the reason why this would be very much helpful to us is because it allows us a mechanism to make this pattern a bit more well, not really a bit more, much more easy to see, in that if there's a power of 2 such that you can rearrange it and it gives you another power of 2, its digit sum will still remain the same. And since its digit sum will still remain the same, that certain number, let's say 2n and 2n plus k, should give the same mod 9, right? So they should leave the same number when they should leave the same remainder when they are divided by 9. So here we can check against their digit sums, because the mod of their digit sum is the same as the mod of the number itself. So well, at first it doesn't really affect it, so this would be 1 mod 9. Okay, so I'm not going to write mod 9 all the time. This would be 2 mod 9, this would be 4 mod 9, this would be 8 mod 9, this would be 7 mod 9, and this would be 5 mod 9. Nothing special up to now. I'm going to draw a line here just so that you'll see why I'm drawing a line here. So this, now the 10 is 1 mod 9, 11 is 2 mod 9, 13 is 4 mod 9, 8 is 8 mod 9, 7 is 7 mod 9, 14 is 5 mod 9, and if I continue on, the next number is 4096. So its digit sum will be 19, which is basically 1 mod 9. Now there's a very clear pattern over here, that we can see that this certain thing repeats, and this is these 6 numbers repeat themselves. So the certain sequence is 1 2 4 8 7 5, right? And then we again see 1 2 4 8 7 5, and then if I had to continue, we would see that 1 2 4 8 7 9. So if we can prove that this sequence of 1 2 4 8 7 9 always holds, then we can prove that there is not such a power of 2 that you rearrange it and it gives another power of 2. The reason being that this pattern holds true for six numbers. So it's a pattern of 6 numbers. So if, let's say, there's a certain 2 here, the only way that I'm getting a 2 again is after I move steps of 6. So the only way, let me write this over, the only way to get the same value mod 9, which we previously saw that if there's a rearrangement, then the two numbers will have the same mod 9. The digit sum of the two numbers will have the same mod 9. So the only way that is possible is if the rearranged number is 2n plus 6, right? So you need to move 6 down, or 6 up, it doesn't really matter, but you need to move steps of 6 in order to get to the same modulo. But we know that between 2n and 2n plus 6, so 2n plus 6 is basically 64 times 2n. Now yes, they have the same modulo 9, but this clearly has more digits than 2n, right? So this would be a contradiction, and therefore there does not exist a number such that there does not exist a power of 2 such that you can rearrange it into a power of 2. Now going back to the last thing that we really need to prove, that this certain pattern holds, again, it's easy to see why this pattern holds. It's because, well, of course, we start from 1 2 4 8 7 5. Now, when we move down, we are really multiplying by 2. Since we are multiplying by 2, the remainder also gets multiplied by 2. So before the remainder was 10, so before the remainder was 5, once we move down, or once we multiplied by 2 to get 2 to the power n plus 1, the remainder is 10, which in the world of module 9 is the same as 1, right? So now we got back to 1. Since we got back to 1, the pattern must repeat, simply because if you have any, let's say A is congruent to B mod 9, then 2A must be congruent to 2B mod 9, right? So if you're multiplying the number by a certain constant, the remainder also gets multiplied by the same constant in mod 9, right? So here you're multiplying by 2, so 1 2 4 8, and then we got 16, which is essentially 7 mod 9, and then you got 32, which is essentially 5 mod 9. So since we get back to our 1 and then we'll continue multiplying by 2, it should give us the same pattern of 1 2 4 8 5, 1 2 4 8 7 5. Once we get to 5, again the same thing happens, that the remainder becomes 10, which is really 1. And since we got to 1, then the same pattern must repeat, because throughout we are really just multiplying by 2, right? So if we are getting 1 again and again, if at any point we get 1, then the other one must be 2, which implies the other one must be 4, which implies the other one must be 8, which implies the other one must be 7, which implies the other one must be 5. Once we get to 5, the remainder becomes 10, which is 1 again. So we got to 1. So the process of getting the same thing repeats. Therefore, the complete proof is really that for a rearrangement to be true, its digit sum must be equal. For its digit sum must be equal, the mod 9 of the two digit sums must also be equal. The mod 9 of the digit sum is the same as mod 9 of the number, as we saw over here, which means that mod 9 of the number must be the same. Now we saw that in order for mod 9 of the numbers to be the same, there has to be a gap of 6 between them. But this is a contradiction, because the maximum gap that you can have before before the number of digits increase, it's 4, right? So when you get to the same value of mod 9, by then the number of digits would have increased. Since the number of digits would have increased, this cannot be a rearrangement, and that's the whole proof, QED. See you in the next video.